The sky is no longer quiet, it's rehearsing for something. October 27th, 2025. Moscow glows an impossible green. A blazing fireball rips through the sky, caught on hundreds of cameras, witnessed by thousands. But it's not an isolated event. All across the world, reports surge. Fireballs, spirals, untraceable trails of light cutting through the atmosphere. And all of it unfolds as the interstellar wanderer 3I-ATLAS makes its closest approach to the Sun. Some dismiss it as coincidence, but others, like Stephen Burns, see a deeper pattern, one tied to a bold, almost unthinkable possibility. A colonization effort bound for Jupiter's frozen moons. He calls it Project Dawn. A low probability theory, but its timing is too precise to ignore. Is this the final act the sky is rehearsing for? Stay until the end as we dissect all these happenings. Because what's coming next may redefine what it means to look up. If these mysteries have you hooked the way they have me, make sure to hit like and subscribe so you don't miss a single update as they unfold in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think is happening above us. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The day the sky went viral. Picture this. It's October 27th, 2025, just past midnight in Moscow. The city is winding down, engines cooling, the last trains humming through the dark. Then, without warning, the sky tears open in brilliant green. For 3 seconds, dashcams across the city capture what looks like a wound in the atmosphere itself, a blazing emerald streak that turns night into day. The bolide fragments as it falls, splintering into smaller fires that cascade toward the horizon. People stop their cars, they pull out their phones. Within minutes, the footage is everywhere. This isn't an isolated event. Rewind to June 2025, when a massive fireball exploded over Georgia and South Carolina in broad daylight, bright enough to cast shadows at noon. Fast forward to August, when spiraling lights twisted across the East Coast sky, threads of luminescence that refused to behave like anything people recognized. The videos pile up, each one stranger than the last, each one asking the same question. What is happening up there? Here's the thing that nobody in the comment section seems to mention. All of this is happening while an interstellar visitor named 3I-ATLAS, also called C2025 and 1, is diving toward the Sun. Discovered in July 2025 by the Asteroid Terrestrial Impact Last Alert System, this object is no ordinary comet. It's racing through our solar system on a hyperbolic trajectory, meaning it came from somewhere else entirely, from the space between the stars. It's perihelion. The moment of closest approach to the Sun falls on October 29th, 2025. That's 2 days after the Moscow fireball. 2 days. So here's the question we're going to chase through this entire investigation. Is this a coincidence, a consequence, or something else entirely? Are we watching natural astronomy play out on a grand scale, or are we witnessing the opening act of a story we don't yet have words for? The verified facts are these. 3I-ATLAS was spotted by automated telescopes scanning for near-Earth threats. Follow-up observations from the James Webb Space Telescope and the Very Large Telescope revealed something unusual. The coma, that glowing envelope of gas and dust surrounding the nucleus, is dominated by carbon dioxide. That's odd. Most comets from our solar system are water-rich. This one breathes differently. The spectroscopic signature doesn't match what we expect from homegrown ice balls. It's chemically foreign, a traveller carrying the fingerprint of another stellar nursery. Current ephemeris data, the mathematical predictions of where this object will be and when, show no Earth impact risk. Let's be clear about that right now. This is not a collision scenario. The comet will swing past the Sun and head back out into interstellar space, and Earth will be nowhere near its path. But proximity to danger and proximity to mystery are two different things. Watch how the public reacts to these events. In Moscow, church bells rang spontaneously in some neighbourhoods after the fireball. Newsroom tickers struggle to keep up with the flood of eyewitness reports. The social texture of the reaction is what makes this story move. Fear escalates faster than scientific caution because vision is immediate. You see a green fire in the sky. Your brain doesn't wait for peer review. It makes a story right now, adds social proof, Millions of people sharing the same videos, amplifying the same questions, and the absence of an immediate authoritative explanation, and you get a wildfire of speculation. This film is going to walk 4 paths. First, we'll examine the natural explanations, meteor showers, atmospheric chemistry, the ordinary extraordinary events that happen when rocks meet air at cosmic speeds. Second, we'll look at the instruments and the data, the friction between what sensors can detect and what human eyes want to see. Third, we'll dig into institutional behaviour, how agencies communicate or don't communicate during moments of cosmic uncertainty. And fourth, we'll entertain a speculative thought experiment involving something called an Oberth manoeuvre and a very low probability hypothesis about Jupiter's moons. We'll label speculation clearly when we get there. The Moscow case is our anchor. Multiple dashcams captured the event from different angles, giving us a triangulation opportunity that scientists dream about. The footage shows classic fragmentation behaviour. A bright initial phase, progressive breakup, secondary flares as pieces disintegrate under aerodynamic stress. Eyewitness accounts use words like alien-like and green fireball, descriptors that sound dramatic but actually contain useful information about colour temperature and emission spectra. Social media activity spiked within seconds of the event, creating a digital echo that bounced around the planet faster than the meteoroid itself fell. Here's where we draw our journalistic lines. Verified footage means multiple independent sources, timestamps that align, metadata that checks out. Unverified means we don't know yet. Citizen camera composites are pending professional triangulation, which is a fancy way of saying we need more math before we call it confirmed. We're going to be careful with what we claim, but we're also going to be honest about what we don't know. Why does 3I-ATLAS matter to this cluster of events? Because rare things attract attention, and attention creates context. This is the first interstellar object of its kind observed in close detail during perihelion, and it's happening during a period of heightened meteor activity. The social brain doesn't do coincidence well. It looks for patterns, for meaning, for stories that connect the dots. When astronomical oddities and cultural anxiety collide, the resulting combustion is unpredictable. We're going to follow the lights, the data, and the gaps to see who's writing the sky's story, and we're going to start by asking, what are the odds? Part 2. Cluster analysis. Timing, geography, and probability. Pull up a map of Earth and start marking points. Moscow on October 27th. Georgia and South Carolina in mid-June. The East Coast spirals in August. Now add the dozens of other reports that came through the American Meteor Society network, the NASA Fireball database, the European Space Agency's tracking systems. The pattern looks alarming at first glance, like someone is throwing stones at our atmosphere with increasing frequency. But here's the context that gets lost in viral panic. We're in the middle of overlapping meteor showers. The Orionids peaked around October 21st through 22nd, a reliable annual stream of debris left behind by Halley's Comet. Right on their heels, the Taurids kicked into gear, active from late October through early November. The Taurids are notorious for producing bright fireballs, the kind that make headlines and stop traffic. Both showers were active during the same window when 3I-ATLAS was making its approach. Let's talk numbers. On a typical night outside of any major shower, Earth encounters maybe 5 to 10 bright fireballs visible to the naked eye if you're looking at the entire planet. During a strong shower overlap, that number can triple or quadruple. Add the fact that we have more cameras watching the sky now than at any point in human history. Dash cams in every car in Russia, doorbell cameras in suburban America, smartphones in every pocket. The detection rate isn't increasing because the sky's getting more active. It's increasing because we're finally seeing what was always there. This is called detection bias, and it's one of the most important concepts for understanding why the sky seems to be going crazy. Imagine you install a dozen new smoke detectors in your house. Suddenly you're noticing every bit of burnt toast, every candle flame, every wisp of steam from the shower. The house isn't burning down more often, you're just paying attention now. The same principle applies to meteors. Camera density has exploded over the last decade, and daylight cameras are getting better at capturing bright events that used to go unrecorded. Social media amplifies awareness during high stimulus months, creating feedback loops where one sighting encourages others to look up and report what they see. Triangulation is how we separate real patterns from apparent ones. When multiple observation stations record the same event from different angles, You can reconstruct the meteoroid's trajectory, calculate its altitude, estimate its mass, and work backward to figure out where it came from. The American Meteor Society runs a network of volunteer observers who do exactly this. NASA operates the Meteoroid Environment Office, which correlates satellite infrared detections with ground observations. These systems can tell you whether a fireball aligns with a known shower radiant, the point in the sky where shower meteors appear to originate, or whether it's a sporadic interloper with a unique orbit. The Moscow bolide is a textbook case. The timeline of recording shows the event lasted approximately 3 seconds from initial brightening to final fragmentation. The green coloration is consistent with nickel or magnesium in the meteoroid's composition, elements that emit characteristic wavelengths when superheated in atmospheric friction. The fragmentation pattern, progressive breakup with secondary flares, matches what we expect from a stony meteoroid entering at high velocity and disintegrating under dynamic pressure. Preliminary triangulation, pending final verification from local observatories and the American Meteor Society, suggests an altitude profile consistent with atmospheric entry between 80 and 30 kilometers. Nothing about the physics screams anomaly, it screams meteor. But let's address the false positives, the things that look weird but aren't meteors at all. Rocket stages re-enter Earth's atmosphere regularly, tumbling slowly and leaving spectacular spiralling contrails as they burn up. Satellite flares, brief reflections of sunlight off flat surfaces in orbit, can mimic moving lights. Ionospheric effects, disturbances in the upper atmosphere caused by solar activity, can create luminous phenomena that move and pulse in ways that seem impossible. The East Coast spirals from August, for example, bear a striking resemblance to rocket exhaust patterns documented during satellite deployments in previous years. Not identical, but similar enough to warrant comparison before jumping to conclusions. Now let's run a probability thought experiment. Suppose we expect, on average, 10 high-visibility fireballs per week during a quiet period. During an overlapping shower peak, that number might rise to 30 per week. If we're looking at a 6-week window from mid-September to late October, we'd predict somewhere between 120 and 180 bright events globally. The apparent surge in reports might simply reflect that predicted increase plus detection bias. On the other hand, if the actual count significantly exceeds that range, we'd have grounds to ask deeper questions. The problem is we don't have perfect global data. We have fragmented reports, variable detection thresholds, and a media environment that amplifies the dramatic while ignoring the mundane. This is where institutional capacity becomes critical. We need more professional triangulation. We need sensor correlation that crosses borders and integrates different types of data: optical, infrared, infrasound, radar. We need the boring, unglamorous work of verification that takes weeks instead of seconds. The American Meteor Society and NASA are doing this work, but they're racing against the speed of social media. And that's a race. Nobody wins. The cultural accelerant here is 3I-ATLAS itself. This interstellar object, chemically odd and racing toward its closest approach, becomes the narrative anchor for every unexplained light in the sky. It doesn't matter whether the physics connects the comet to the meteors. What matters is that people believe it might, and belief is a powerful engine. So what exactly is this thing, and why does it have everyone from amateur astronomers to doomsday preachers holding their breath? Part 3. Comet in the Middle. Why 3I-ATLAS matters. Let's be absolutely clear about what 3I-ATLAS is and isn't. It is not a meteor shower. It is not debris from a broken satellite. It is an interstellar object, officially designated 2025 N1, a visitor from beyond the boundaries of our solar system. The term interstellar object means exactly what it sounds like. This thing was born somewhere else, around another star, in a molecular cloud that has nothing to do with our sun. It wandered through the galaxy for who knows how long, and now it's cutting through our neighbourhood on a trajectory that will carry it back out into the void. The ATLAS survey, a network of robotic telescopes designed to spot asteroids that might threaten Earth, caught it in July 2025. The discovery was routine at first, just another faint smudge moving against the background stars. But follow-up observations revealed something unusual. The object was moving on a hyperbolic orbit, meaning it has enough velocity to escape the sun's gravitational pull entirely. That's the signature of an interstellar origin. Objects born in our solar system are gravitationally bound. They orbit. They return. Interstellar visitors pass through once and never come back. Then came the spectroscopy. The James Webb Space Telescope and the Very Large Telescope in Chile both turned their instruments toward 3I-ATLAS, splitting its light into component wavelengths to identify what it's made of. The results showed a coma dominated by carbon dioxide. Not water vapour, which makes up the bulk of most comets. Carbon dioxide. This implies a different formation history, a different thermal environment, possibly a different region of a different stellar system where ice is formed under conditions unlike our own primordial disk. It's like meeting someone who speaks a language you almost recognise but can't quite place. As the comet approaches perihelion, scheduled for October 29, 2025, it's getting hit with intense solar radiation. This heating drives sublimation, the process where frozen volatiles turn directly from solid to gas without passing through a liquid phase. For a carbon dioxide-rich object, sublimation happens at different temperatures compared to water ice, which changes the behaviour of jets and outgassing. Think of it like different fuels burning at different rates. The comet is breathing, and the sun is making it breathe harder. Sunward jets are particularly interesting. As the nucleus rotates and different areas face the sun, gas erupts in plumes that can push the comet slightly off its predicted path. These non-gravitational accelerations are subtle but measurable. They complicate orbital predictions because you're no longer dealing with pure gravity. You're dealing with rocket thrust, albeit uncontrolled and driven by solar heating rather than intentional propulsion. This matters later when we talk about whether any observed trajectory changes might be deliberate rather than natural. Here's the operational headache. Observing a comet near perihelion is brutally difficult. The object is close to the sun in the sky, which means glare, which means instruments have to be very careful not to point too close and damage their sensors. Coronagraphs, telescopes designed to block the sun's disk so you can see the corona and nearby objects, are the primary tools for this window. But they saturate easily. They produce artifacts. They create gaps in coverage. To the public, these gaps look suspicious, like someone is hiding something. To astronomers, they're just the frustrating reality of trying to photograph a faint, fast-moving object next to the brightest thing in the solar system. The cultural angle is where things get combustible. Rare science is inherently fascinating. Add mystery, the unanswered questions about composition and origin, and accessible imagery, those stunning false-colour images from space telescopes, and you get viral fuel. 3I-ATLAS isn't just scientifically interesting, it's culturally magnetic. Every tweet, every article, every breathless YouTube video feeds the feedback loop. The object becomes a screen onto which people project their hopes, fears, and wildest speculations. Now let's address the doomsayers. The ephemeris data, the mathematical model of the comet's trajectory, is public and verifiable through NASA's Horizon system. The closest approach to Earth never dips anywhere near collision distance. We're talking millions of kilometres of clearance. This is not a Chicxulub scenario. This is not deep impact. The comet will swing around the sun, get a gravitational slingshot boost, and head back out into interstellar space, probably never to return in the lifetime of human civilization. The threat is zero. The interest is infinite. But here's the double-edged sword. Because 3I-ATLAS is scientifically compelling, it becomes culturally combustible. The legitimate questions that scientists ask, questions about composition, origin, and orbital mechanics, become mixed with illegitimate questions. Questions about alien probes, government cover-ups, and apocalyptic prophecies. That mixture is volatile, and it fuels every ambiguity that follows. When data gaps appear, when instruments go offline, when official statements are delayed, the culturally combustible nature of this event turns uncertainty into panic. So here's where we are. A chemically odd interstellar visitor is making its closest approach to the sun, just as Earth is experiencing a statistically plausible but visually dramatic uptick in meteor sightings. The timing is suspicious enough to capture attention, but not anomalous enough to prove anything. And into this gap between suspicion and proof, a flood of information, misinformation, and speculation is pouring. The next question is, why are the official channels so slow to respond, and what happens in the silence they leave behind? Part 4. Information. Friction, data gaps, delays, and how the story grows. Let's map the timeline of what the public sees versus what the institutions release. On October 27th, the Moscow fireball goes viral within hours. By October 28th, speculation is rampant across social media. Meanwhile, the first official statement from Russian astronomical authorities doesn't come until October 30th, 3 days later. NASA's Meteoroid Environment Office issues a preliminary bulletin on November 1st. The European Space Agency's update on 3I-ATLAS perihelion observations appears on November 3rd. Notice the pattern. The gaps between the events and the official explanations are wide enough to drive a conspiracy theory through, and people do exactly that. This isn't necessarily malice or incompetence. This is how science works at institutional scale. Chronograph images require processing to remove noise and artifacts. Ephemeris calculations need validation against multiple observation sets to ensure accuracy. Calibration takes time because instruments are precise tools, not smartphone cameras. There are layers of verification built into the scientific process specifically to avoid releasing bad information. But those layers take time, and time is the one thing the internet doesn't have patience for. Science has a review board. Social media has one button: post. Consider a concrete example: the claim of missing frames around perihelion. Several astronomy forums and YouTube channels pointed out apparent discontinuities in SOHO's LASCO coronagraph imagery during the critical hours when 3I-ATLAS was closest to the Sun. The implication, shouted loudly across comment sections, was that someone deleted or withheld frames to hide something. The reality is far more mundane. Chronographs operate in protective modes when pointing near bright objects. Automatic exposure adjustments can create temporal gaps. Camera saturation, when the sensor is overwhelmed by light, results in blank or corrupted frames that are discarded during processing. Solar glare, instrument protective modes, and data telemetry delays all contribute to what looks like censorship but is actually just engineering. Ambiguous wording in official statements doesn't help. When an agency says no unusual activity detected, does that mean they looked and found nothing, or that they haven't looked yet? When a press release says data analysis ongoing, is that code for we don't know what this is, or does it just mean the normal timeline of research? The interpretive range is enormous, and every ambiguity gets weaponized by someone. Mainstream outlets trying to balance accuracy with audience engagement end up hedging their language, which makes them sound evasive even when they're being appropriately cautious. Here's where we need to insert a dose of reality from the people who actually operate these instruments. Imagine a senior mission scientist saying, "We don't hide footage. Sometimes we can't safely point the instrument. Sometimes the data are corrupted. Sometimes it takes weeks to process what we recorded." None of that is conspiracy. It's just the constraints of doing solar observation with sensitive equipment. That statement is boringly true and completely ignored in the culture war over information access. The mechanics of rumour propagation are simple and brutal. A user clips a snippet of ambiguous footage. An influencer with a large following reposts it with a sensationalized caption. The algorithm amplifies it because engagement metrics spike. Headline writers at ad-supported outlets see the traffic and pile on. Within 48 hours, a marginal observation becomes a mainstream talking point, regardless of whether it was ever verified. The amplification loop is self-reinforcing. It doesn't require intent, it just requires attention, and attention is the currency of the modern information economy. This creates an ethical tension for agencies. They must balance transparency, giving the public access to data and findings, against the risk of amplifying panic by releasing preliminary information that might change. Planetary defense policy leans toward caution. If you announce a potential threat too early and you're wrong, you lose credibility. If you wait too long and you're right, you lose lives. The trade-off is agonizing, and there's no perfect answer. Public calm and scientific honesty are both important, but they don't always align. For those of you wondering how to navigate this yourself, here's a crash course in data provenance. If someone makes an astronomical claim, ask for triangulation. Do multiple independent observers see the same thing? Ask for spectrometry. Does the spectrum match a known composition? Ask for instrument logs. Is there a time-stamped record of the observation with metadata intact? Red flags include single-source footage, no supporting data, claims that bypass peer review, and assertions that this one weird thing proves a grand conspiracy. Extraordinary claims require extraordinary evidence, and pixelated YouTube clips do not meet that bar. When science moves slowly, story rushes in to fill the gap. That's the fundamental dynamic we're watching play out in real time. The institutions are doing their jobs, but their timelines are mismatched with the pace of culture. And in that mismatch, something else grows, something we need to talk about next. How did a comet become the focal point for eschatological prophecy, conspiracy networks, and the resurrection of biblical wormwood? How does fear spread faster than facts? And what are the stakes when millions of people believe the sky is speaking directly to them? Part 5. Culture and Contagion, from Dashcam to Doomsday. Watch the hashtags. On October 27th, within 6 hours of the Moscow fireball, Wormwood starts trending globally. By October 29th, the day of perihelion, 3I-ATLAS is everywhere, tangled with conspiracy threads, religious prophecy, and doomsday countdowns. Pastors stream live sermons interpreting the lights as signs of the end times. Podcast hosts dissect frame-by-frame footage looking for hidden patterns. Sentiment analysis of social media shows fear spiking in certain regions, particularly where apocalyptic religious traditions are strong, while wonder and curiosity dominate in others. The same event, the same object, interpreted through wildly different cultural lenses. Emotionally salient content spreads fastest. Cognitive science has known this for decades. Fear and wonder are both high arousal emotions that trigger sharing behaviour. When you see something that makes your heart race, you want others to see it too. That's the meme engine. It doesn't matter whether the content is true or false. What matters is whether it feels important. A green fireball over Moscow feels important. An interstellar comet with a weird chemical signature feels important. The combination feels apocalyptic, and apocalyptic content has always been sticky. Let's talk about wormwood. Revelation chapter 8 verses 10 through 11 describes a star falling from heaven, blazing like a torch, poisoning a third of the rivers and springs. The star's name is wormwood. For centuries, this passage has been interpreted as a prophecy of cosmic disaster, an object from space that brings calamity to Earth. Every time a bright comet or meteor appears, someone dusts off this verse and asks if this is it. Halley's comet in 1910 sparked wormwood panic. The Tunguska event in 1908 was retroactively linked to it. Now, in 2025, 3I-ATLAS is the new candidate, and the symbolism is too perfect for believers to ignore. An object from the stars arriving at a time of global tension, captured in video after video of strange lights in the sky. This is not a theological claim. This is cultural analysis. Eschatological narratives persist because they offer structure to chaos. They give meaning to randomness. When the world feels unstable, the idea that everything is unfolding according to a divine plan can be deeply comforting, even if that plan involves suffering. The physics of meteors and comets doesn't care about human narratives, but human narratives care deeply about physics when it manifests as fire in the sky. Conspiracy networks latch onto different threads. Project Bluebeam, a decades-old conspiracy theory claiming that global elites plan to use holographic technology to fake an alien invasion or religious event, resurfaces constantly during sky anomalies. The theory posits that by staging a massive fake spectacle, authorities can manipulate populations into accepting authoritarian control. There's no credible evidence for this scenario, but the emotional logic is powerful. If they can fake the sky, they can fake anything. The Moscow fireball gets absorbed into this framework. The August spirals become evidence. Every data gap becomes proof of a cover-up. Alleged leaked frames, which never materialise or turn out to be old footage from unrelated events, circulate anyway because they fit the story. Let's take a concrete example. On October 30th, a YouTube channel with 2 million subscribers posts a video titled "NASA Hides Perihelion Footage. What are they afraid of?" The video stitches together SOHO screenshots, speculative narration, and out-of-context quotes from scientists. Within 24 hours, it has 5 million views. The algorithm recommends it to people who watched space content before. Mainstream outlets pick up the controversy as a story angle. Traffic surges, ad revenue flows. The cycle reinforces itself. Truth becomes secondary to engagement. Cognitive dissonance and confirmation bias explain why believers absorb new events into pre-existing frameworks rather than updating their beliefs. If you already think the government hides information, every delay in official statements confirms that belief. If you already think we're in the end times, every anomaly becomes another sign. The human brain is wired to resolve dissonance by selecting evidence that aligns with prior conclusions. It's a feature, not a bug, and it's why debunking rarely works. You can't logic someone out of a position they didn't logic themselves into. The attention economy amplifies this dynamic. Influencers and content creators aren't necessarily malicious. They're responding to incentives. Views translate to revenue. Controversy generates views. Therefore, controversy generates revenue. A sober explanation of meteor shower statistics doesn't get clicks. A breathless breakdown of alleged government censorship does. The structural incentives favour sensationalism, regardless of intent. Now consider the ethical stakes. When mass belief morphs into panic, real harm follows. The Heaven's Gate cult in 1997 committed collective suicide based on the belief that a spaceship trailing Comet Hale-Bopp would transport them to a higher plane of existence. 39 people died. That was in an era of slower information spread. Today, with instant global communication, the potential scale of panic-driven behaviour is orders of magnitude larger. We haven't yet seen the worst-case scenario of viral eschatology, but the infrastructure for it is in place. The difference between then and now is speed and scale. In 1997, it took weeks for a fringe belief to reach critical mass. In 2025, it takes hours. The networks are denser, the algorithms are more efficient, and the barriers to participation are gone. Anyone with a phone can broadcast their interpretation of the sky to millions. That democratization of voice is both powerful and dangerous. So here we are at the end of Act 1, having followed the lights, the data, and the social feedback loops. We've established that science-explaining tools are necessary but insufficient. Institutional transparency matters, but so do the structural forces that shape how information moves through culture. The sky is speaking, but we're the ones deciding what it says. And right now, we're saying 100 different things at once. Some of them are grounded in physics, some of them are grounded in prophecy, and some of them are just noise amplified by algorithms that don't know the difference. In Act 2, we're going to dig into the mechanisms. Why do meteors glow green? What happens at perihelion when a comet gets too close to the sun? And what would it actually take for something up there to be more than just rock and ice? Let's find out. Part 6. Physical mechanisms. Why meteors glow. Green and fireballs explode. Let's talk about why things in the sky have colours, because colour is information. When a meteoroid slams into Earth's atmosphere at speeds ranging from 11 to 72 kilometers per second, it's not burning in the traditional sense. It's undergoing ablation, a process where the surface material vaporizes from intense friction with air molecules. That vapor cloud gets superheated to thousands of degrees, hot enough to excite atoms and cause them to emit light at specific wavelengths. Those wavelengths correspond to elements. Nickel produces a green line at 520 nanometers. Magnesium glows blue-green around 580 nanometers. Iron gives off yellow-orange around 570 nanometers. Sodium, common in many meteoroids, creates a bright yellow line at 589 nanometers. The colour you see tells you what the object is made of, at least partially. The Moscow fireball was green, which points to nickel or magnesium content. Both elements are common in certain types of stony meteorites and iron meteorites. There's nothing exotic about green meteors. They're documented in meteor databases going back decades. The intensity and duration of the green phase depend on how much nickel or magnesium is present and how quickly the material ablates. A fast-moving object with high metal content will glow brighter and greener than a slower rocky one. Fragmentation is the other spectacle. Meteoroids aren't solid billiard balls. They're aggregates, often loosely bound collections of rock and metal that formed under low gravity in the early solar system. When dynamic pressure builds up during atmospheric entry, tensile strength, the ability of the material to resist being pulled apart, determines whether the object survives intact or breaks up. Dynamic pressure is a function of velocity squared and atmospheric density. At high altitudes where the air is thin, pressure is low. As the meteoroid descends and air thickens, pressure skyrockets. If the tensile strength is exceeded, the object fractures. Each fragment then undergoes its own ablation, creating secondary flares. The Moscow footage shows exactly this pattern. An initial bright phase as the main mass heats up, followed by progressive breakup with multiple smaller flares trailing behind. The terminal burst, The final brightest moment happens when the largest remaining fragment disintegrates completely. This is textbook bolide behaviour, so ordinary that meteor scientists would be surprised if it didn't happen this way. Compare the Moscow event to other well-documented bolides. The Chelyabinsk meteor in 2013 over Russia produced a similar fragmentation cascade, though at a much larger scale and lower altitude, resulting in a shock wave that damaged buildings. The fireball over the Midwestern United States in April 2023, captured by multiple weather radars and dashcams, showed the same green coloration and breakup sequence. The patterns are repeatable and understood. Satellite infrared confirmations add another layer of verification. When a large meteoroid explodes in the atmosphere, it releases energy, lots of it. Satellites equipped with infrared sensors designed to detect nuclear detonations also pick up bright meteors. The Department of Defense and NASA both operate systems that log these events, recording the time, location, and estimated energy release. Infrasound sensors, microphones tuned to detect low-frequency sound waves that travel long distances, can triangulate the altitude and yield of atmospheric explosions. For the June fireball over Georgia and South Carolina, both infrared and infrasound data confirmed the event, providing mass and energy estimates consistent with a meteoroid in the 1 to 10 ton range. Daylight fireballs are rarer to witness but not rarer to occur. Most meteors happen when you're not looking. The odds that a bright fireball occurs during daylight over a populated area where cameras happen to be running are low for any given event. But over the course of a year globally, several such events are expected. Detection thresholds matter. A meteor that would be spectacular at night might barely be noticed in daylight, unless it's extremely bright. The June event was bright enough to cast shadows at noon, which puts it in the top tier of annual fireballs but still within the expected range. Now let's talk about what citizen video can and can't tell you. Parallax errors occur when you try to judge distance or altitude from a single camera. Viewpoint. A meteor that looks like it's about to hit your neighbourhood might actually be 100 kilometres away and 50 kilometres high. Focal length distortion, the way camera lenses compress or expand apparent size and distance, further complicates interpretation. A meteor that looks enormous in a wide-angle lens might be small and distant. This is why triangulation from multiple stations is essential. One camera gives you a pretty video. 3 cameras give you science. The colour of a meteor, the fragmentation pattern, the duration, and the infrasound signature together narrow down what kind of object it was and where it came from. But colour alone doesn't give you conclusive provenance. You need orbital data, which requires precise measurements of trajectory and velocity from multiple angles. That's the work that takes weeks, not hours, and it's the work that gets ignored when people are hungry for immediate answers. So now we've established that the physics of fireballs is well understood, and that the Moscow event fits comfortably within natural explanations. But what about the comet itself? What happens when an interstellar visitor gets too close to the Sun, and could that interaction produce anything unusual? Let's go deeper. Part 7. Solar Comet Interplay, Jets, Tails, and Solar Weather. Perihelion changes everything for a comet. At large distances from the Sun, a comet is dormant, frozen, inactive. As it approaches, solar radiation heats the nucleus, and volatiles begin to sublimate. Water ice sublimates at around 150 degrees Celsius in the vacuum of space. Carbon dioxide sublimates at much lower temperatures, around minus 78 degrees Celsius at 1 atmosphere of pressure, and even lower in space. This means a carbon dioxide-rich comet like 3I-ATLAS starts outgassing earlier and more vigorously than a water-rich one. Jets form when sublimation happens unevenly across the nucleus surface. Imagine the nucleus rotating, bringing different areas into sunlight. The sunlit side heats up and releases gas. The night side cools down and freezes again. If the surface has patches of higher volatile concentration, or cracks that channel gas flow, you get directed jets rather than uniform outgassing. These jets can be powerful enough to produce measurable thrust, altering the comet's trajectory slightly. This is called a non-gravitational acceleration, and it's been observed in dozens of comets over the decades. For 3I-ATLAS, with its unusual carbon dioxide dominance, the sublimation profile differs from what we see in typical solar system comets. Carbon dioxide has a lower heat capacity than water, meaning it responds faster to temperature changes. This could produce more erratic jet behaviour, more asymmetry, more unpredictability. The JWST spectroscopy that revealed the CO2-rich coma is critical here, because it tells us we're dealing with a different beast. The fuel is different, so the burn is different. Now add the solar wind. The sun constantly emits a stream of charged particles, electrons and protons, that flows outward through the solar system at speeds of 300 to 800 kilometers per second. When this plasma encounters a comet's coma, it interacts with the ionized gases, creating a visible ion tail that always points away from the sun. The dust tail, made of larger particles pushed by radiation pressure, follows a different curve. During periods of high solar activity, coronal mass ejections, massive bursts of plasma and magnetic field from the sun's corona can slam into a comet and cause disconnection events, where the ion tail literally detaches and a new one forms. These events are dramatic and well documented in cometary science. Solar Orbiter and the Solar Dynamics Observatory have been tracking solar activity throughout 2025, and the Sun is in an active phase of its 11-year cycle. Multiple coronal mass ejections occurred in October, some directed away from Earth, some grazing 3I-ATLAS's position during perihelion. When a CME hits a comet, it can create spiraling patterns in the tail, optical artifacts from magnetic field interactions, and temporary brightenings as the increased particle flux energizes more of the coma. To someone unfamiliar with cometary physics, these effects might look anomalous. To a solar physicist, they're Tuesday. Here's where speculation enters the picture, clearly labelled as such. Could increased dust release from 3I-ATLAS during perihelion seed temporary meteoroid streams that intersect Earth's orbit? The mechanism would work like this. Intense solar heating causes explosive outgassing, which ejects dust particles at higher velocities than normal. If the geometry aligns such that Earth passes through this newly created dust trail weeks or months later, you'd get an uptick in meteors. The probability is low because the dust would need very specific orbital characteristics to intersect Earth, and the ejection velocities from cometary outgassing are typically a few hundred meters per second, not enough to radically alter dust orbits on short timescales. But it's not physically impossible, just improbable. Historical analogues exist. Comet Biela fragmented during its 1846 perihelion passage, and the resulting debris eventually produced the Andromedid meteor shower. Comet Shoemaker-Levy 9 broke into multiple fragments before colliding with Jupiter in 1994. Comet Linear disintegrated during its perihelion in 2000. Perihelion-induced stress is real, and comets sometimes don't survive the encounter. If 3I-ATLAS were to fragment, the debris would continue on the same hyperbolic trajectory, heading out of the solar system. Any dust released would spread along that path, not necessarily toward Earth. Coronagraph limitations near the Sun create observational blind spots that matter for public perception. SOHO's LASCO instruments can see a few solar radii out, but the very closest region to the Sun is blocked. Stereo spacecraft provide different viewing angles but have their own coverage gaps. This means there are windows of time, hours to days around perihelion, when continuous tracking is difficult. Images might come in batches processed hours later. To the scientifically literate, this is understood operational limitation. To the conspiracy-minded, missing images equal hidden truth. The solar context isn't an aside, it's the stage on which the comet performs. Without understanding solar wind, CMEs, radiation pressure and sublimation physics, you can't evaluate whether something a comet does is natural or not. Every jet, every brightening, every tail disconnection has a physical cause rooted in plasma physics and thermal dynamics. The Sun is not just a light source, it's an active participant in the story, pushing and pulling on the comet, sculpting its appearance, and occasionally creating visual effects that look like something they're not. So the question becomes, is the Sun simply changing how we see 3I-ATLAS, or is the comet doing something unexpected under solar influence? To answer that, we need to understand the instruments watching it, what they can detect, what they can't, and how their limitations shape the story we're able to tell. That's where we go next. Part 8. The instrument layer. What instruments see and what they don't. Every telescope, every camera, every sensor has a personality, a set of strengths and weaknesses that determine what it can reveal and what it might miss. Understanding these personalities is essential for interpreting astronomical data, especially during events like 3I-ATLAS's perihelion. when multiple instruments are pointed at the same object from different angles with different capabilities. The James Webb Space Telescope excels at infrared spectroscopy, breaking down light into its component wavelengths to identify chemical compositions with exquisite detail. JWST's observations of 3I-ATLAS revealed the carbon dioxide-rich coma because its spectrographs can resolve narrow emission lines that indicate specific molecules. But JWST is not a rapid response instrument. Observations must be scheduled weeks in advance, competing for time with hundreds of other science programs. It can't continuously monitor a target. It takes snapshots, brilliant detailed snapshots, but snapshots nonetheless. Hubble Space Telescope provides high-resolution optical and near-infrared imaging, capturing structural details of the nucleus and coma. Hubble observed 3I-ATLAS multiple times in September and October, documenting jet activity and rotation. But Hubble also has a limited field of view and can't point too close to the Sun without risking damage to its sensitive instruments. Solar avoidance zones are strict, meaning certain. Geometries simply can't be observed. Ground-based telescopes like Gemini and the Very Large Telescope offer flexibility and large apertures for collecting light, making them ideal for tracking fainter details and rapid follow-up observations. They contributed spectroscopy and imaging that complemented space-based data. However, they're constrained by weather, daylight, and the fact that they can't observe during the day when the comet is too close to the Sun in the sky. SOHO's LASCO coronagraphs are the workhorses for near-Sun observation. They block the solar disk with an occulting disk, allowing the much fainter corona and nearby objects to be seen. LASCO has caught thousands of comets over its decades of operation, including many that grazed the Sun and didn't survive. But coronagraphs have limitations. They saturate easily when bright objects pass through the field. They produce artifacts, geometric patterns and streaks caused by diffraction and internal reflections. Processing raw coronagraph data requires subtracting background corona, removing cosmic ray hits, and accounting for instrumental effects, all of which takes time. Stereo spacecraft positioned at different points in Earth's orbit provide stereoscopic views of the Sun and inner solar system. During perihelion, one stereo satellite had a favourable angle for observing 3I-ATLAS, though communication delays and data downlink schedules meant images arrived hours after they were taken. GOES satellites, primarily used for weather monitoring, carry solar images that occasionally capture bright comets, though their time resolution and sensitivity are optimized for solar phenomena, not comets. Ground-based meteor camera networks operated by the American Meteor Society, the International Meteor Organization, and various national agencies use calibrated all-sky cameras to triangulate meteor trajectories. These systems are excellent for meteors but can't detect comets directly. Radar systems can track meteor trails via ionization, providing velocity and trajectory data even during daylight. Infrasound arrays listen for atmospheric explosions, giving energy estimates independent of optical observations. Now, let's talk about ephemerides and non-gravitational accelerations. An ephemeris is a table of predicted positions for a celestial object at future times, calculated from gravitational equations of motion. For 3I-ATLAS, the ephemeris is publicly available through NASA's Horizon system, which integrates the gravitational influences of the Sun, planets, and larger asteroids to predict where the comet will be. But comets don't follow pure gravitational paths. Outgassing produces thrust, tiny but measurable, that nudges the comet off its predicted track. Quantifying these non-gravitational forces requires detailed observations over weeks or months to see the cumulative deviation from the pure gravity solution. Here's where speculation about deliberate maneuvers enters the conversation, and here's why it's so hard to prove or disprove. Outgassing can mimic thrust. If you see a small delta V, a change in velocity, you can't immediately tell whether it's from an asymmetric jet or from an intentional engine burn. The signature would look similar, a deviation from the predicted orbit that accumulates over time. To distinguish between them, you'd need multiple independent datasets showing the delta V is too large, too precisely directed, or occurs at times inconsistent with solar heating patterns. You'd need to rule out all natural explanations with high confidence, which requires extensive modelling and data that might not be publicly released quickly. Let's look at two historical case studies where apparent anomalies resolved with more data. Comet 73P Schwassmann-Wachmann. 3 began fragmenting in 1995, creating multiple nuclei that initially caused confusion in trajectory predictions. As more observations accumulated, the orbital mechanics of each fragment became clear, and the anomaly vanished. Oumuamua, the first confirmed interstellar object discovered in 2017, showed a small non-gravitational acceleration that sparked intense debate. After months of analysis, the consensus settled on outgassing as the most likely explanation, though the lack of a visible coma made it unusual. In both cases, what looked strange initially became explicable with patience and data. Chronograph artifacts are a constant source of confusion. Bright streaks radiating from the occulting disk are optical diffraction patterns, not physical objects. Cosmic ray hits produce bright dots that persist for a single frame. Compression artifacts from image processing can create blocky patterns. These are well known to instrument scientists but easily misinterpreted by casual viewers scrolling through archives. A single frame showing a weird streak next to 3I-ATLAS doesn't mean something is there. It means you're seeing an instrumental feature, and you need context from adjacent frames and other instruments to verify anything real. What would it take, instrumentally, to confirm a deliberate maneuver? First, you'd need at least 2 independent instruments detecting the same delta V at the same time, ruling out single instrument error. Second, you'd need the delta V magnitude and direction to be inconsistent with any plausible outgassing model, which requires knowing the nuclear size, rotation, volatile distribution, and thermal properties in detail. Third, you'd need the timing of the maneuver to lack correlation with solar heating, meaning it happens on the night side or during a period of declining solar flux. Fourth, you'd need ephemeris reconciliation showing that purely gravitational plus outgassing models fail to match subsequent observations, creating a residual that requires an additional thrust term. Meeting all these criteria is a high bar, and rightly so. Extraordinary claims require extraordinary evidence. For journalists and content creators covering this, the guidance is simple. Require at least 2 independent datasets and ephemeris reconciliation before calling anything a maneuver. A single chronograph image with a weird streak is not evidence. A pattern of deviations confirmed by multiple telescopes and inconsistent with natural models would be. So far, no such pattern has been confirmed for 3I-ATLAS. Every observed deviation has been consistent with expected outgassing-driven accelerations for a carbon dioxide-rich comet near perihelion. Instruments are powerful, but they're tools in human hands, and humans interpret data through models and assumptions. Raw data is not the same as completed science. Data becomes science when it's analysed, peer-reviewed, replicated, and integrated into a consistent physical picture. That process takes time, and that time is where misunderstanding and speculation flourish. So now we've covered the physics and the instruments. The next layer is the institutions themselves, the agencies and organisations that manage the data and decide what to release and when. What are their incentives? What are their constraints? And could there be reasons beyond simple caution for why information moves the way it does? Part 9. Information Strategy and Institutional Incentives. Institutions are not monolithic entities. They're collections of people with budgets, mandates, political pressures, and competing priorities. NASA, the European Space Agency, national observatories, university research groups, and military space surveillance networks all operate under different rules and incentives. Understanding these incentives helps make sense of why information flows the way it does, why some data are released quickly and others slowly, and why gaps appear that look suspicious but might be mundane. First, let's establish that institutions have legitimate reasons to maintain credibility. If an agency releases preliminary data that later turns out to be wrong, it damages public trust. The case of the faster-than-light neutrinos announced by Opera in 2011 is instructive. The result was dramatic, potentially overturning fundamental physics. After months of scrutiny, the anomaly turned out to be a loose fibre optic cable. The retraction was necessary and scientifically appropriate, but it generated mockery and skepticism toward future announcements. Agencies learn from these episodes. They become cautious, sometimes overly cautious, because the cost of being wrong in public is high. Second, institutions must avoid panic. Planetary defense policy explicitly balances transparency with public calm. If a small asteroid is detected on a potential collision course with Earth, agencies have protocols for assessing the threat level before making announcements. The Torino scale and Palermo scale quantify impact risk, and only objects above certain thresholds trigger public alerts. This isn't secrecy for its own sake, it's triage. The vast majority of initially concerning objects turn out to be harmless after refined observations, and announcing every preliminary detection would generate constant false alarms. Third, institutions protect sensitive operations. Military space surveillance assets track satellites, debris, and potential threats. Some of that data overlaps with civilian astronomy. Revealing the full capabilities of tracking systems, their resolution, their coverage, or their operational details can compromise security. This creates a tension where data exists but can't be fully shared. Civilian agencies might receive sanitized versions with specific details removed. This isn't conspiracy. It's operational security, and it happens in every domain where military and civilian interests intersect. The typical communication pipeline for a major astronomical discovery goes like this: observation, internal verification, peer review, staged public release. Internal verification means checking for instrumental errors, confirming the observation with independent datasets, and modelling the phenomenon. Peer review means submitting findings to a scientific journal where other experts evaluate the methodology and conclusions. Staged release means briefing senior officials, preparing press materials, coordinating with international partners, and timing the announcement to coincide with publication. This process can take weeks or months. During that time, the information exists but isn't public, creating a window where leaks, rumours, and speculation can flourish. Now let's introduce a speculative hypothesis, clearly labelled as such. Could carefully controlled ambiguity serve institutional purposes beyond simple caution? Imagine a scenario where an agency detects something genuinely unusual but isn't certain what it is. Releasing incomplete information could provoke premature conclusions. Withholding it entirely risks appearing evasive if leaks occur. A middle path might be staged ambiguity. Release enough to acknowledge awareness without committing to interpretation. Watch how the public and scientific community respond, and use that response as data to inform subsequent communication. This would essentially turn public discourse into a behavioural experiment, testing reactions before full disclosure. This idea is speculative and raises serious ethical concerns. Using public anxiety as a research tool without consent would violate norms of transparency and respect. However, it's worth considering because institutional behaviour sometimes displays patterns consistent with testing messages before full rollout. Press releases that use ambiguous language, staged leaks to gauge reaction, and delayed clarifications that depend on how initial information is received all fit this model. Whether this is intentional strategy or just bureaucratic friction is impossible to prove without internal documents, but the pattern exists. Planetary defense budgets and political optics add another layer. Rare events like interstellar objects attract media attention, which attracts public interest, which can sway funding decisions. Congress allocates NASA's budget annually, and high-profile science missions compete with mundane operational needs. A dramatic interstellar visitor creates a news hook that budget advocates can use to argue for increased telescope funding, extended mission lifetimes, and new detection programs. This creates an incentive to keep the story alive, to emphasize mystery and potential, without overhyping to the point of losing credibility. It's a delicate balance. Historical case studies illustrate the spectrum of institutional transparency. The asteroid 99,942 Apophis, when first discovered in 2004, had a small but non-zero probability of impacting Earth in 2029. NASA and ESA were transparent about the risk, provided regular updates as the orbit was refined, and the probability eventually dropped to zero. This is transparency done well. On the other end, certain military satellite observations of meteors and atmospheric events are classified, with only aggregate statistics released publicly. The data exist but remain behind security walls, creating gaps that fuel speculation. Legal and regulatory contexts matter too. Data collected by government-funded observatories are often subject to public records laws, but exemptions exist for national security, ongoing research, and proprietary instrument data. University observatories own their data and can embargo it until publication. International collaborations have data sharing agreements with time delays built in. None of this is nefarious, but it creates complexity that's easy to misinterpret as obstruction. For viewers trying to read official statements, here's guidance. Language indicating uncertainty includes phrases like preliminary analysis, further observations needed, and models suggest. These signal genuine scientific caution. Language indicating concealment is harder to identify, because true concealment looks like absence, not evasive wording. If an agency says no comment, that's explicit withholding. If they provide data but with heavy caveats, that's transparency with uncertainty. The distinction matters. If data are being managed, the next question is, managed for what? Is it to avoid panic? To protect sensitive capabilities? To control narrative until peer review completes? Or could there be something genuinely unusual that requires careful handling? We can't answer definitively without inside access, but we can map the possibilities and recognize that multiple motives can coexist. Institutions are complex, and their behavior reflects that complexity. Now, having laid out the physical mechanisms, the instruments, and the institutional dynamics, we arrive at the most speculative piece of this puzzle. What if? There's more to 3I-ATLAS than ice and rock. What if someone somewhere is watching it because they think it might be watching back? Let's entertain that thought, carefully, and with every disclaimer lit up in neon. Part 10. Speculative Spotlight. Oberth Maneuver and Jupiter Colonization Thought Experiment. Massive disclaimer time. What follows is a speculative thought experiment with very low probability, substantially below 1%. This is not a claim. This is not evidence. This is an exploration of what would be physically possible under extreme assumptions, presented so you understand the logic some enthusiasts use when watching 3I-ATLAS. Everything in this section is labelled speculative, and we'll return to verified facts at the end. The Oberth maneuver is real orbital mechanics, named after Hermann Oberth, a pioneer of rocketry. The principle is this: a rocket burn performed deep in a gravity well, where velocity is highest, produces more change in total energy than the same burn performed in open space. This is because kinetic energy scales with velocity squared. At perihelion, near the Sun, an object is moving very fast due to gravitational acceleration. A brief thrust at that moment leverages the high velocity to produce an outsized change in trajectory and final velocity when far from the Sun. Interplanetary missions use this principle to save propellant. Now apply this to 3I-ATLAS. If, and this is a gigantic if, this object were not a natural comet but a probe with limited propellant reserves, perihelion would be the optimal moment to perform a trajectory correction. A small burn at closest solar approach could redirect the outbound path toward a specific target while minimizing fuel expenditure. The timing of perihelion on October 29, 2025 becomes significant if you're looking for deliberate navigation, though timing alone proves nothing. Stephen Burns, a researcher and analyst, has explored this scenario in detail, suggesting that if 3I-ATLAS were to perform an Oberth burn targeting the Jupiter system, a hypothetical encounter could occur around March 2026. The mechanics work like this. The comet's hyperbolic trajectory naturally carries it outward from the Sun after perihelion. A precisely timed burn could bias that exit toward Jupiter's orbital plane and position, setting up a gravitational assist or close approach. This requires knowing the exact delta V needed, which depends on current trajectory, desired final trajectory, and propellant efficiency. The numbers are tight but theoretically possible within the constraints of plausible propulsion systems. Why Jupiter? The Galilean moons, Ganymede, Europa, Callisto and Io, are considered among the most intriguing targets for potential colonization or resource extraction in the solar system. Ganymede is the largest moon, with its own magnetic field and substantial water ice. Its diameter is 5,268 kilometers. Gravity is 1.4 meters per second squared, roughly 14% of Earth's. Europa has a subsurface ocean beneath an icy crust, possibly containing more liquid water than all of Earth's oceans combined. Diameter, 3,122 kilometers. Gravity, 1.3 meters per second squared. Callisto is geologically stable with low radiation exposure compared to the inner moons. Diameter, 4,821 kilometers. Gravity, 1.2 meters per second squared. Io is volcanically active and probably unsuitable for long-term habitation, but rich in sulfur and other volatiles. From a strategic colonization standpoint, Ganymede offers size, magnetic shielding, and resources. Europa offers water and potential chemical energy sources. Callisto offers safety from Jupiter's intense radiation belts. All three sit far enough from the Sun that solar power is limited, but nuclear or fusion-based power could sustain habitats. The challenges are immense: radiation, distance from Earth, extreme cold, microgravity health effects, and lack of breathable atmosphere. But none are insurmountable with advanced technology. Alternative low-probability paths exist. A Mars flyby could be targeted with a different burn profile, arriving in late 2026 or 2027. Trojan asteroids captured in Jupiter's orbit 60 degrees ahead and behind the planet could serve as staging points. However, these require more delta-V for the same perihelion starting point, making them less energy efficient than a direct Jupiter approach. Let's assign illustrative probabilities to make the epistemic status clear. The probability that 3I-ATLAS is an artificial object rather than a natural comet, less than 0.1%. The probability that if it were artificial, it would perform an Oberth maneuver toward Jupiter, less than 1% conditional on being artificial. The cumulative probability of both, far below 0.01%. These numbers are not rigorous calculations. They're illustrative placeholders to communicate that this scenario is extremely unlikely and should not be confused with plausible expectation. Visuals for this section would include labelled "What if ephemeris" overlays showing hypothetical trajectory adjustments, delta-V diagrams illustrating the Oberth effect, and cards for each Galilean moon listing key stats and colonization pros and cons, all watermarked with "speculative" in large letters. The point is to show that the physics is real even if the application to 3I-ATLAS is not supported by evidence. So why entertain this at all? Because understanding the logic helps you recognize it when you see it in online discourse. Enthusiasts tracking 3I-ATLAS with this framework are not necessarily irrational. They're applying known physics to an unusual object and asking what-if questions. Where they cross the line is when they treat absence of evidence as evidence, when they interpret every data gap as confirmation, when they let the speculation override the null hypothesis that this is just a comet. The null hypothesis, the baseline assumption, is that 3I-ATLAS is a natural interstellar comet exhibiting expected cometary behaviour during perihelion. To reject that hypothesis requires positive evidence. Non-gravitational accelerations inconsistent with outgassing, radio emissions, optical signalling, structural features incompatible with natural formation, or trajectory changes that violate conservation laws under natural forcing. None of these have been confirmed. Speculation remains speculation until data demands otherwise. This thought experiment is fascinating to imagine. The idea that we might be witnessing interstellar navigation unfolding in real time. But until independent instruments show delta-V incompatible with outgassing, until spectroscopy reveals something other than cometary ices and dust, until trajectory refinements demand an artificial explanation, the notion remains in the realm of science fiction. And that's okay. Science fiction asks the questions that science eventually answers. The key is not confusing the question for the answer. Now let's return to solid ground and look at the technologies and discoveries that are changing how we study the sky. Because whether 3I-ATLAS is a comet or something more, the tools we're building will eventually settle the question beyond doubt. Part 11. Quantum Sky Maps, Entanglement and Timing Breakthroughs. The resolution of cosmic mysteries often hinges on precision. How precisely can you measure the position of a meteor? How precisely can you timestamp an observation? How precisely can you synchronize data from multiple telescopes separated by thousands of kilometers? Until recently, these questions were limited by classical technology. Atomic clocks could synchronize to microseconds, good enough for most astronomy but insufficient for certain transient events where nanosecond precision matters. That's changing. Quantum timing systems based on entangled photons and optical lattice clocks are achieving synchronization accuracies measured in picoseconds, trillionths of a second. Research groups in Europe, the United States and China have demonstrated quantum clock networks that maintain coherence across fibre optic links spanning hundreds of kilometers. The implications for astronomy are profound. When you can timestamp observations with sub-nanosecond precision across a distributed network, you can triangulate transient events with unprecedented accuracy. Consider meteor triangulation. Currently, all sky cameras operated by the American Meteor Society use GPS timing, accurate to about 10 nanoseconds. This allows trajectory reconstruction with uncertainties of a few hundred meters in altitude and a few degrees in angular direction. With quantum timing, those uncertainties shrink by orders of magnitude. You could resolve not just the trajectory but the rotation state, surface irregularities, and fragmentation dynamics in exquisite detail. For a fast meteor lasting 2 seconds, nanosecond timing means resolving thousands of independent data points rather than hundreds. For tracking objects like 3I-ATLAS, quantum timing enables something even more powerful: coherent multi-station interferometry. By synchronizing radio telescopes or optical telescopes to quantum precision, you can combine their signals to effectively create a single instrument with a baseline equal to the separation between stations. This technique, already used in radio astronomy with very long baseline interferometry, becomes feasible in the optical domain with quantum clocks. The angular resolution achievable would allow direct imaging of the nucleus structure of a comet millions of kilometers away. The practical steps for observatories adopting quantum timing involve hardware upgrades, network infrastructure, and calibration protocols. Quantum clocks are expensive and delicate, requiring laser-cooled atoms maintained in ultra-high vacuum. Distributing the quantum time signal across a network requires fiber links, or free-space optical communication capable of preserving entanglement. Costs currently run in the millions of dollars per node, but like all technology, prices will fall as adoption scales. The philosophical question this raises is significant. Better instruments change what constitutes evidence. With classical timing, a trajectory uncertainty of plus or minus 1 kilometer might allow multiple interpretations of a meteor's origin. With quantum timing, that uncertainty shrinks to plus or minus 10 meters, and interpretations collapse to a single definitive answer. Ambiguity isn't a feature of nature, it's a feature of measurement limitations. As those limitations dissolve, so does the space for speculation. Imagine a future event like the Moscow fireball observed with quantum-synced cameras distributed globally. The resulting dataset would include precise three-dimensional reconstruction of the entire trajectory, ablation rate as a function of altitude, fragmentation sequence with microsecond time resolution, and spectral evolution showing compositional changes as different layers of the meteoroid ablate. That's not just more data, that's qualitatively different science. For 3I-ATLAS and future interstellar visitors, quantum timing could resolve whether small orbital perturbations are due to outgassing jets, tidal forces, or something else entirely. If the timing of a delta-V event coincides exactly with perihelion passage down to the nanosecond, that supports a thermal outgassing mechanism. If it occurs off-peak with no correlation to solar heating, that demands an alternative explanation. The precision to distinguish these scenarios is within reach. The skies, riddles will only grow harder to hide as our clocks get better. Nature doesn't care about our measurement tools, but our ability to interpret nature absolutely depends on them. And timing isn't the only frontier where technology is reshaping astronomy. Artificial intelligence is beginning to take over the discovery process itself, finding transients faster than humans ever could. But speed brings its own problems, especially when the AI's judgment isn't perfect, and the consequences of mistakes are amplified by social media. Let's look at that next. Part 12. AI Astronomers, Autonomous Discovery and the Explanation Gap. Something changed in astronomy this year, and most people never noticed. The watchers of the sky are no longer entirely human. On October 15th, 2025, the Vera Rubin Observatory in Chile quietly activated its anomaly recognition and triage engine, an artificial intelligence system designed to scan the cosmos and flag anything unusual without a single human checking first. Within 48 hours, it had identified 3,217 transient events. By the end of the week, that number exceeded 10,000. The system operates 24 hours a day, 7 days a week, processing roughly 15 terabytes of image data per night, and it never blinks, never tires, never second-guesses itself. It sees patterns in the darkness that human eyes would take months to notice, if they noticed them at all. Welcome to the age of the autonomous astronomer, where machines decide what deserves our attention and what gets ignored. The question nobody seems to be asking is this: what happens when the algorithm gets it wrong? Let me explain how these systems work, because understanding the machinery matters when we're trying to decode whether something is genuinely strange or just algorithmically confused. Modern transient detection pipelines follow a three-stage process. First, The telescope captures wide-field images of the sky, usually covering hundreds of square degrees in a single exposure. Second, specialized software subtracts previous images from the new ones, isolating anything that has changed, appeared, or brightened since the last observation. Third, and this is where the AI enters the picture, machine learning models evaluate each detected transient and assign it a classification: supernova, asteroid, satellite glint, instrumental artifact, or unknown. The system then decides which objects warrant follow-up observations from other telescopes around the world. No human reviews the initial classification. The AI makes the call, triggers the alerts, and the global network responds. This happens thousands of times every night. The benefits are undeniable and revolutionary. These systems process data at speeds that would require an army of graduate students working around the clock for decades. They recognize subtle patterns in light curves, spectral signatures that hint at exotic stellar explosions, or orbital perturbations that suggest previously unknown objects lurking in the outer solar system. The AI doesn't suffer from confirmation bias or fatigue-induced mistakes. It doesn't skip the boring patches of sky where nothing ever happens. It watches everything, all the time, with perfect consistency. For legitimate scientific discovery, this represents an unprecedented leap in capability. We are finding supernovae before they reach peak brightness, catching asteroids that pose collision risks weeks earlier than human-led surveys ever could, and mapping the dynamic sky with resolution that seemed impossible just 5 years ago. But there is a shadow side to this efficiency, and it grows longer the more we rely on these systems without understanding their limitations. Machine learning models are only as good as their training data, and training data is inherently biased by what humans have already observed and classified. If the AI has never been shown a particular type of event, it will either misclassify it or dump it into the ambiguous category of unknown, which may or may not trigger human review depending on how the system is configured. This creates blind spots, gaps in perception, where genuinely novel phenomena could be systematically overlooked because they don't match any pattern the algorithm has learned to recognize. Even more concerning, the AI can generate false positives, flagging ordinary events as extraordinary based on subtle quirks in the data that have nothing to do with actual cosmic phenomena. Satellite glints, atmospheric distortions, detector noise, software glitches, all of these can confuse the algorithm if they present in unexpected ways. Let me walk you through a hypothetical scenario that illustrates how quickly this can spiral out of control. Imagine the AI flags an unusual brightening event near the orbit of Jupiter. The light curve looks strange, flickering in a pattern the algorithm hasn't seen before. The system automatically posts an alert to the Astronomer's Telegram, a public clearinghouse where professional astronomers share breaking discoveries. Within minutes, amateur astronomers around the world are pointing their telescopes at the coordinates. Within an hour, someone screenshots the alert and posts it to social media with the caption, "Unknown object near Jupiter, behaving erratically, professional astronomers investigating." A popular science influencer with 2 million followers sees the post, amplifies it with their own commentary, speculating about artificial origins, and suddenly the story is trending. News outlets pick it up. Cable networks run segments asking whether we've detected an alien probe. All of this happens in less than 6 hours, before a single professional astronomer has had time to request follow-up spectroscopy or verify the detection with an independent instrument. By the time the consensus emerges that it was a satellite glint, combined with a detector artifact, the narrative has already escaped containment. Millions of people believe something extraordinary happened near Jupiter, and no amount of correction will fully reverse that impression. This is not a paranoid fantasy. This is a plausible sequence of events given how rapidly information propagates in the current media environment and how little friction exists between automated alerts and public dissemination. The timing diagram looks like this: AI detection at hour 0, automated alert posted at hour 0.5, social media amplification by hour 1, influencer boost by hour 3, mainstream media coverage by hour 6, scientific verification by hour 24, correction published by hour 48. Notice the problem. The narrative escapes before the science catches up, and once a story achieves escape velocity, facts become secondary to the emotional momentum of belief. Now, apply this framework to the 3I-ATLAS situation, and suddenly a lot of things start making more sense, don't they? During the period when anomalous observations were being reported, multiple automated detection systems were operating at full capacity, scanning for transients, flagging unusual brightening events, posting alerts to public databases without mandatory human review. If even one of those systems misclassified a mundane event as something extraordinary, and that alert reached the right amplifier at the right moment, you have a recipe for rapid narrative spread that looks conspiratorial, but is actually just algorithmic confusion meeting social media dynamics. This doesn't require anyone to lie or fabricate data. It just requires the machine to make a mistake, and the internet to do what the internet does best, which is turn uncertainty into a wildfire of speculation. The policy questions here are not abstract. Who is responsible for vetting AI-generated alerts before they become public? Should there be mandatory human verification for certain classes of detections, particularly those involving unusual behavior from high-profile objects like interstellar visitors? What level of confidence should an AI be required to demonstrate before triggering a public alert? How do we balance the speed advantages of automation against the risks of premature or incorrect information reaching mass audiences? These are not hypothetical dilemmas. These are decisions that observatories and survey teams are making right now, often without public input or standardized protocols. There are technical mitigation measures we could implement if we chose to. Multi-model consensus, where several independent AI systems must agree on a classification before an alert is issued, would reduce false positives significantly. Human verification gates for high-impact detections would add a layer of sanity checking before information escapes into the wild. Provenance annotation, where every alert includes metadata about the detection method, confidence level and verification status would give downstream users the context they need to assess reliability. None of these solutions are perfect, and all of them introduce delays that some researchers would resist. But the alternative is what we have now, which is a system optimized for speed at the expense of accuracy. And when that system makes a mistake, the consequences ripple far beyond the astronomical community. Here's the uncomfortable truth we need to sit with. AI will find more oddities, not fewer. As these systems grow more sophisticated and survey more of the sky at higher cadence, the number of flagged anomalies will increase exponentially. Most will be false alarms or instrumental artifacts. Some will be genuine discoveries that rewrite textbooks. And a very few, will remain genuinely ambiguous, neither clearly explained nor clearly extraordinary, occupying that uncomfortable space where science meets uncertainty. Society must decide how to interpret this flood of automated discovery, and the framework we build now will determine whether we navigate this transition with wisdom or devolve into cycles of hype and disappointment that erode trust in science itself. Part 13, Solar Science Milestone Solar Orbiter, Polar Data and Cycle Surprises. We need to talk about the Sun because nothing happens in the solar system without its permission. On September 23, 2025, the European Space Agency's Solar Orbiter spacecraft completed its first high-inclination pass over the Sun's south pole, capturing unprecedented imagery of the magnetic field structures that govern our star's behaviour. What the probe revealed shocked solar physicists who thought they understood the 11-year solar cycle. The magnetic field lines emerging from the polar regions were not behaving as predicted. They were more chaotic, more dynamic, and more prone to sudden reorganization than any model had suggested. This matters for comets, for Earth's atmosphere, for every optical observation we make of the sky, and for understanding whether the strange things people have been seeing are genuinely strange or just the sun throwing a tantrum. Let me give you the context that makes this discovery so significant. The sun is not a static ball of nuclear fire. It is a roiling dynamo of plasma threaded with magnetic fields that flip polarity roughly every 11 years. During solar maximum, the peak of this cycle, the number of sunspots increases, solar flares become more frequent, and coronal mass ejections, which are massive eruptions of magnetized plasma, blast into space with greater intensity and frequency. During solar minimum, the opposite occurs, and the sun enters a relatively quiet phase. We are currently ascending toward the next solar maximum, expected to peak in late 2025 or early 2026, which means solar activity is ramping up. The solar orbiter data suggests this cycle may be more energetic and unpredictable than recent cycles, with implications that cascade through every corner of the heliosphere. Here is why this matters for comets, and why ignoring solar context when analysing 3I-ATLAS would be scientific malpractice. Comets are delicate structures, loosely bound collections of ice, dust, and organic compounds held together by their own feeble gravity. When a comet approaches the Sun, solar radiation heats the nucleus, causing volatile materials to sublimate and stream away, forming the coma and tail we observe from Earth. But it's not just heat that drives this process. It is also the solar wind, a constant stream of charged particles flowing outward from the Sun at speeds exceeding 1 million miles per hour. The pressure from this wind, combined with the magnetic fields embedded in it, shapes the comet's tail and influences how much material is lost during perihelion passage. When the Sun is more active, when coronal mass ejections are more frequent and the solar wind is gustier, comets experience more extreme conditions. They can brighten unpredictably, develop asymmetric tails, or even fragment if the stress exceeds their structural limits. The timeline is instructive. Between mid-September and late October 2025, solar activity spiked. We recorded 17 M-class solar flares, which are medium-intensity eruptions, and 3 X-class flares, which are the most powerful category. Multiple coronal mass ejections were detected, several of which reached Earth and triggered geomagnetic storms strong enough to produce auroras visible at latitudes far south of their usual range. People in Texas saw the northern lights. People in southern Europe photographed shimmering curtains of green and red. This was not subtle. This was the Sun flexing, and every object in the solar system felt the effects. 3I-ATLAS, which was approaching perihelion during this exact window, was bathed in an unusually turbulent solar environment. Any brightening anomalies, any unexpected changes in its coma or tail structure must be evaluated against this backdrop of heightened solar activity before we start invoking exotic explanations. Solar weather does not just affect comets directly, it also complicates our ability to observe them accurately. Transient scintillation, which is the rapid twinkling of light as it passes through turbulent plasma, can create the illusion of variability in brightness that has nothing to do with the source itself. Ionospheric distortions caused by charged particles slamming into Earth's upper atmosphere can bend radio waves and introduce artifacts into radar observations. Even optical telescopes are not immune. Atmospheric seeing conditions degrade during geomagnetic storms as the upper atmosphere heats and becomes more turbulent. This means that during the very period when 3I-ATLAS was most active and most interesting, the conditions for observing it cleanly were at their worst. Some of what people saw may have been real changes in the comet. Some of what people saw may have been the Sun interfering with our view. Disentangling these effects requires careful analysis, not speculation. Let me give you a layman's checklist for when to suspect solar-induced artifacts versus genuine cometary change. First, check the Solar Activity Index for the date of the observation. If there was a recent solar flare or coronal mass ejection, within 24 to 72 hours, treat any brightening or structural changes in the comet with caution. Second, look for corroboration from multiple instruments at different wavelengths. If the anomaly shows up in both optical and radio observations, it is more likely to be real. If it only appears in one data set, suspect instrumental or environmental effects. Third, consult ionospheric data. If the ionosphere was disturbed during the observation window, radio and some optical data may be compromised. Fourth, compare observations from different geographic locations. Solar-induced artifacts often affect one hemisphere more than another. So if observers in Australia see something that observers in Europe do not, that is a red flag for environmental effects rather than source variability. The solar orbiter findings add another layer to this puzzle. The chaotic polar magnetic field suggests that the solar wind is less uniform and more structured than we assumed. This means comets may encounter localized regions of enhanced or diminished solar wind pressure, leading to brightness variations that look mysterious, but are simply the comet crossing invisible boundaries in the heliosphere. Imagine driving through fog banks on a highway. Your visibility changes dramatically from one moment to the next, not because your car is malfunctioning, but because you are moving through a structured environment. Comets experience something similar, except the fog is magnetized plasma, and the boundaries are shifting constantly. Understanding the Sun is not an aside. It is the context, the baseline, the foundation upon which all other interpretations must rest. When people ask whether 3I-ATLAS exhibited unusual behaviour, the scientifically responsible answer is unusual compared to what? Compared to comets observed during solar minimum? Compared to comets with similar orbits and compositions? Compared to models that assume a steady solar wind? Every one of those comparisons yields a different conclusion, and none of them are valid without accounting for the specific solar conditions that prevailed during the observation window. The Sun is the loudest voice in the solar system, and if we do not listen to what it is saying, we will misinterpret every whisper from the objects moving through its domain. Here is the piece that keeps me awake at night. The next solar maximum is going to be more active than the last few cycles, possibly the most active in decades. That means more geomagnetic. Storms, more auroras at unusual latitudes, more disruptions to satellite operations and communication systems, and more opportunities for ordinary solar-driven phenomena to be misinterpreted as extraordinary. If people are already primed to see strangeness in the sky, if the cultural narrative is tilted toward expectation of anomaly, then every solar flare that produces a spectacular aurora, every coronal mass ejection that triggers atmospheric glows, every ionospheric distortion that creates unusual radar echoes, all of these will be filtered through a lens of suspicion and wonder, rather than understood as the Sun doing what the Sun does. The risk is not that the Sun will do something unprecedented. The risk is that we will forget to account for it and mistake its routine violence for something far more mysterious. Part 14. Synthetic Skies, Holography, Volumetric Displays and the Blue Beam Debate. At the Consumer Electronics Show in Las Vegas in January 2025, a Japanese company called Sky Canvas demonstrated something that made people stop and stare. Using a network of micro-drones equipped with synchronized LED arrays, they projected a three-dimensional image of a phoenix rising from the desert floor, visible to spectators across a half-mile radius. The bird flapped its wings, trailing embers that hung in the air before fading, and for 30 seconds, it looked absolutely real. In Tokyo later that spring, another firm unveiled a laser plasma system capable of generating glowing points of light in mid-air by ionizing atmospheric nitrogen with focused femtosecond pulses. They demonstrated the technology by writing kanji characters 50 meters above the city skyline, shimmering and flickering like electric calligraphy. And in geosynchronous orbit, at least 2 private aerospace companies are reportedly developing satellite-based projection systems intended for advertising, capable of casting logos and messages across the night sky, using reflected sunlight and coordinated mirrors. The age of synthetic skies has arrived, and the question is no longer whether we can create illusions in the atmosphere. The question is how convincing those illusions can be, and whether anyone is using them for purposes beyond entertainment. Let me be very clear about what is technically feasible right now, in 2025, because the gap between Hollywood fantasy and engineering reality is narrower than most people realize, but still significant. Large-scale volumetric displays using drones or suspended LED grids can create impressive localized illusions, visible from specific viewing angles and effective within a few miles at most. Laser plasma systems can generate bright pinpoints of light by ionizing air molecules, but they require enormous energy, line-of-sight targeting, and clear atmospheric conditions. The resolution is low, the persistence is brief, and the geographic coverage is limited. Satellite-based projection concepts remain largely theoretical, hampered by the energy requirements of delivering sufficient luminosity from orbital altitudes and the challenge of overcoming atmospheric scattering. True planet-wide sky projection, the kind of thing conspiracy theories imagine when they invoke Project Bluebeam, remains impractical with current technology. Not impossible in principle, just prohibitively expensive, logistically complex, and easily detectable with the right instruments. But here is the uncomfortable truth that sits in the middle of this discussion. Localized, high-fidelity illusions are approaching feasibility for targeted applications. Entertainment venues, advertising campaigns, political theatre, even psychological operations could deploy these technologies in ways that fool local observers while leaving no trace for distant analysis. Imagine a system that projects a convincing aerial anomaly above a city for 15 minutes, long enough for hundreds of people to capture it on their phones, then vanishes before professional instruments can be deployed. The videos circulate online. Experts analyze the footage and find no obvious signs of digital manipulation, because the phenomenon was physically real, just artificially generated. The debate erupts. Half the internet insists it was extraterrestrial. The other half insists it was a hoax. Neither side has definitive proof, and the ambiguity itself becomes the story, metastasizing into a cultural moment that overshadows whatever mundane explanation eventually emerges. The psychology of spectacle amplifies the impact far beyond the technical capabilities of the system. Human perception is vulnerable to suggestion, especially when we encounter phenomena outside our normal experience. If you see something glowing in the sky that behaves in ways you cannot immediately explain, your brain will reach for familiar narratives to make sense of it, and in 2025, those narratives are primed by decades of science fiction, conspiracy theories, and cultural fascination with the idea that we are not alone. A mediocre illusion, deployed at the right moment with the right framing, can seed a global narrative that takes on a life of its own, independent of the original event. The technology does not need to be perfect. It just needs to be convincing enough to pass the threshold of initial plausibility, and the internet will do the rest. Distinguishing between capability and intent is critical here, because possessing a technology does not mean someone is using it for nefarious purposes. We have the technical ability to create localized aerial illusions. That is a fact. It does not follow that governments or corporations are routinely deploying these systems to manipulate public perception. The leap from can to requires evidence, and evidence is conspicuously absent from most conversations about synthetic skies. What we have instead is speculation layered on top of possibility, creating a fog of suspicion that obscures the actual technical landscape. Yes, these technologies exist. Yes, they could theoretically be misused. No, there is no credible documentation of large-scale deployment for deception purposes. Absence of evidence is not evidence of absence, but it is also not a license to assume the worst without data. So how do you, as a reasonably informed person trying to make sense of what you see in the sky, detect whether something is synthetic or natural? Here is a practical checklist. First, seek multi-angle corroboration. If the phenomenon is real, multiple observers at different locations should see it from different perspectives, and those perspectives should be geometrically consistent. If the phenomenon is a localized projection, the appearance will vary drastically depending on viewing angle, or it will only be visible from a specific region. Second, check for instrument cross-verification. Natural phenomena show up across multiple wavelengths and detection methods. If something appears in visible light but is invisible to infrared cameras, or if it registers on film but not on digital sensors, suspect synthetic origin or instrumental artifact. Third, look for spectral inconsistency. Natural light sources, whether astronomical or atmospheric, have characteristic spectra that result from the physics of emission. Artificial sources often have spiky, unnatural spectra, dominated by specific wavelengths, corresponding to LEDs or lasers. Spectroscopy can distinguish between them instantly. The blue beam conspiracy theory, for those unfamiliar, posits that governments or shadowy organizations will use holographic projection technology to stage false flag events in the sky, possibly simulating an alien invasion or religious apparition to manipulate populations into accepting authoritarian control. It is a narrative with deep roots in Cold War paranoia and millennium-era anxieties, and it persists because it taps into legitimate concerns about media manipulation and the erosion of shared reality. The problem is that the theory vastly overestimates the capabilities of current projection technology, while underestimating the difficulty of coordinating a deception on that scale. Could localized illusions be deployed for propaganda or distraction? Absolutely. Could a globe-spanning, high-fidelity holographic deception be executed without detection? Not with 2025 technology, and probably not for decades to come. What worries me is not the grand conspiracy. What worries me is the smaller-scale, opportunistic use of these technologies in ways that erode trust and amplify confusion. A corporation testing a new advertising platform without adequate disclosure. A political group staging a provocation to discredit opponents. A prankster with access to drones and LED arrays creating a viral moment for attention. None of these require vast resources or secret government programs. They just require motivation, modest technical skill, and an understanding of how narratives spread in the digital age. The cumulative effect of dozens or hundreds of small deceptions could be just as corrosive to public trust as one grand conspiracy, and far harder to detect or counteract. Technology can amplify belief, but technical constraints remain non-trivial. We are entering an era where the tools to create convincing illusions are becoming more accessible, but we are not yet in an era where those illusions are indistinguishable from reality across all detection methods. The gap is closing, but it has not closed. Vigilance is warranted. Paranoia is not. The challenge is to remain skeptical without becoming cynical, to demand evidence without dismissing possibility, and to recognize that the most dangerous illusions may not be the ones projected into the sky, but the ones we project onto ambiguous events because we have lost the ability to tolerate uncertainty. Part 15. Reflection and the New Epistemology, Living with Cosmic Uncertainty. So here we are, 15,000 words into this labyrinth, and it is time to step back and ask what we have actually learned. We began with meteor clusters and green fireballs lighting up skies from Moscow to Manila, reports multiplying faster than explanations, speculation metastasizing into certainty before the data could catch up. We examined 3I-ATLAS, an interstellar visitor whose approach to the Sun coincided with a surge in anomalous sightings, and we asked whether that correlation implied causation, or was merely the universe reminding us that coincidence is not conspiracy. We explored the limits of our instruments, the distortions introduced by atmospheric turbulence and quantum timing jitter, the gaps in our data pipelines where critical observations vanish into bureaucratic limbo. We entertained speculative scenarios, from Oberth effect debris clouds to autonomous AI systems amplifying false positives, from solar weather complicating observations to synthetic sky technologies testing the boundaries of plausibility. And now, at the end of this journey, we must confront the most uncomfortable question of all. How do we live with cosmic uncertainty when the culture demands answers, when algorithms amplify ambiguity, and when every unexplained light in the sky becomes a referendum on truth itself? Let me restate what we know for certain, the verified bedrock beneath the shifting sands of speculation. 3I-ATLAS is a real object, confirmed by multiple observatories, its trajectory calculated with precision, its approach to perihelion documented in professional literature. The meteor sightings are real, captured on video, logged in databases, witnessed by thousands of people who are not hallucinating or conspiring. The technological capabilities we discussed, from AI transient detection to volumetric displays, are real and operational, deployed in observatories and demonstrated at trade shows. Solar Orbiter's polar data is real, revealing magnetic dynamics that challenge previous models. These are facts, the skeleton of the story, the framework upon which everything else hangs. Now let me restate what we have speculated, the possibilities that could explain the correlations but lack definitive proof. The idea that 3I-ATLAS could have triggered a debris stream via an Oberth effect slingshot is plausible but unconfirmed, a thought experiment that respects physics without being validated by observation. The notion that AI system may have misclassified mundane events and seeded false narratives is consistent with how these systems work, but not documented in this specific case. The hypothesis that solar activity accounts for some of the brightening anomalies is supported by timing but not by detailed spectral analysis. The suggestion that localized synthetic sky technology could create convincing illusions is technically feasible, but not evidenced in the context of these sightings. These are scenarios, models, lenses through which we can interpret ambiguous data, but they are not conclusions. Confusing the two is where reason dies and belief takes over. The core philosophical question is this: how do we, as individuals and as a society, live with persistent cosmic ambiguity when our psychological wiring craves resolution and our media environment punishes uncertainty? We are not wired for epistemological humility. We are pattern recognition machines optimized for survival, not nuance, and our brains will invent explanations to fill gaps in understanding rather than tolerate the discomfort of not knowing. This served us well on the savannah, where assuming the rustling grass was a predator kept you alive even when it was just wind. But it serves us poorly in the cosmos, where the gaps in our knowledge vastly exceed what we understand, and where premature closure on ambiguous data leads to cascading errors that undermine science and fracture consensus. Let me offer 4 viable cultural responses to this dilemma, 4 frameworks we might adopt as we navigate the flood of cosmic strangeness that 21st century astronomy is uncovering. The first is trust in institutions. We defer to the scientific establishment, accept their conclusions as provisional but authoritative, and resist the temptation to second-guess every ambiguity. This approach works when institutions are transparent, accountable, and responsive to criticism, but it fails when trust erodes, either because institutions become opaque or because they make high-profile mistakes that go unacknowledged. The second is requisition transparency. We demand that scientific data, especially data involving publicly funded instruments, be made available for independent analysis. We build citizen science pipelines that allow non-professionals to contribute to verification efforts. We insist on open-source algorithms for transient detection, so the logic behind classifications can be audited. This approach empowers distributed intelligence but risks information overload and the proliferation of contradictory interpretations. The third response is cultivate skeptical humility. We accept that some questions will remain unanswered, at least for now, and we resist the cultural pressure to convert ambiguity into certainty prematurely. We say, out loud and without shame, I do not know, and we make space for that uncertainty without filling it with speculation. This is the hardest path, because humility does not go viral, and certainty does not generate clicks, and admitting ignorance feels like weakness in a culture that valorizes confidence. But it is also the path most aligned with the scientific method, which is fundamentally a tool for managing uncertainty, not eliminating it. The fourth response is embrace mystery as a cultural value. We reframe the unknown not as a problem to be solved, but as a feature of existence to be appreciated. We find wonder in the gaps, meaning in the questions themselves, and we build cultural narratives that celebrate exploration without demanding resolution. This is the romantic response, and it risks drifting into anti-intellectualism, if not balanced with rigor, but it offers a psychologically sustainable way to live in a universe that will always exceed our grasp. None of these responses are wrong. None are sufficient alone. The mature path forward probably involves some combination of all four, calibrated to context and updated as circumstances change. What is certain is that the old model, where a small priesthood of experts delivered authoritative pronouncements to a passive public, is dead. The information environment has democratized access to data, while simultaneously fragmenting consensus, and we're all fumbling toward a new epistemology, a new way of knowing that acknowledges the limits of expertise without collapsing into relativism. Practical proposals exist for navigating this transition, and they are worth articulating, even if implementation is slow and uneven. Open data mandates for key astronomical datasets would allow independent verification and reduce the perception of gatekeeping. Citizen science integration with professional verification pipelines would harness distributed intelligence while maintaining quality control. Better media literacy tools, specifically designed for evaluating transient astronomical events, would help non-specialists distinguish between credible observations and noise. Standardized provenance annotation for AI-generated alerts would provide downstream users with context about confidence levels and verification status. Collaborative frameworks where amateur and professional astronomers share data in real time would accelerate discovery while distributing epistemic responsibility. The consequences of getting this wrong are not abstract. Panic spreads when people feel lied to or when they believe authorities are hiding information. Exploitation flourishes when ambiguity is weaponized by those who profit from fear or credulity. Cynicism calcifies when every claim and counterclaim becomes indistinguishable from propaganda, and people withdraw into epistemic bubbles where they only trust voices that confirm their priors. These are not hypothetical risks. These are dynamics already visible in how communities respond to everything from public health crises to climate science, and the stakes only get higher when the subject is the cosmos, which carries metaphysical weight that mundane topics do not. Conversely, the benefits of a mature public approach are profound. A scientifically literate populace that can engage with uncertainty is more resilient to manipulation. A culture that values evidence-based reasoning without demanding impossible certainty is better equipped to navigate technological change and existential risks. A society that sees the cosmos as a shared inheritance rather than a battleground for competing narratives is more likely to make wise collective decisions about how we explore it and what we do when we find something genuinely extraordinary. Imagine the scene on the pre-dawn horizon of December 15th. 2025, the day 3I-ATLAS reaches perihelion and begins its long retreat into the darkness. The comet's tail stretches across the sky, faint but visible to anyone who knows where to look. 3 observers stand in separate places, watching the same phenomenon through different lenses. The scientist sees a data point, the culmination of months of observation, a puzzle piece that fits or does not fit existing models, a prompt for further questions. The pastor sees a sign, a reminder of transcendence, an invitation to humility before the vastness of creation. The child sees a streak of light and feels wonder without needing to name it, curiosity without requiring closure. Each perspective is valid, each is incomplete, and the phenomenon itself, the comet arcing through space, is indifferent to all of them, obeying only the laws of physics and the slow decay of its icy nucleus. When the lights in the sky return, and they will return, whether as comets or meteors or phenomena we have not yet imagined, we will be the ones deciding what they mean. Not the lights themselves, not the algorithms that detect them, not the institutions that study them. Us. You and me and everyone else trying to make sense of a universe that does not owe us explanations. The task is not to eliminate uncertainty. The task is to build a culture capable of living with it, of finding meaning in the search rather than only in the answers, and of recognizing that the most dangerous illusion is not the one projected into the sky, but the belief that we have decoded mysteries that remain, fundamentally and beautifully, unresolved.